Making a relatively short video on the Chinese Remainder Theorem. This is to help my students on a homework problem on this on the Chinese Remainder Theorem, and I picked this example from the textbook so that students can read along with me. That's on page 76 of our textbook. So the problem is x is congruent to 3 mod 7, x is congruent to 5 mod 15. Notice the GCD of 7 and 15 is 1. That's how the Chinese remainder theorem is supposed to work. So I'll be doing this problem and describe the theorem briefly without getting into the details of the proofs of it, so that you can follow, understand how to solve the problem. All right, now so the problem is x is congruent to 3 mod 7, and it's also congruent to 5 mod 15. So that number must be congruent to 3 mod 7 and also congruent to 5 mod 15. So if x is supposed to be congruent to 3 mod 7, then x can be any one of the following numbers. It could be a negative number such as -4, or maybe 3, because 3 is congruent to 3 mod 7, or 10 is congruent to 3 mod 7, or 17, 24, 31. I'm adding, you notice that I'm adding 7 to the previous one to get the next one. 38, 45, 52, 59, 66, plus 7 is 73, plus 7 is 80, 87, 94, and so forth. And if x is congruent to 5 mod 15, then x should be one of the following. It could be a negative number, or 5, or 20, 35, 50, 65, 80, 95, and so forth. And now you notice that there is a common value between in this list and also the next list. Notice that 80 is really congruent to 3 mod 7 as well as 5 mod 15. If we continue the search, the next number we get is 80 plus 105. You may notice that 105 is 7 times 15. So the theorem will say that if we have x is congruent to a mod n and x is congruent to b mod m, there is a unique solution, mod n times m. Okay, well, let's see how this works. Okay, so if x is congruent to 3 mod 7, then x must be 3 plus 7k for some integer k. Right? So it must be a multiple of 7 plus 3 to be congruent to 3 mod 7. Right? But x is also congruent to 5 mod 15. So we're going to stick this number here into this equation. X is congruent to 5 mod 15. That means that 3 plus 7k must be congruent to 5 mod 15. If we can solve for k in this equation, then we can find k and then put it in here, and that would give us the value of x. Well, this is not too hard to do. 7k is congruent to 5 minus 3 mod 15. Okay, meaning that 7k is 2 mod 15. So one more thing we need to do is find the inverse of 7 mod 15 and multiply out to get the value of k. Well, I'm thinking out loud here. I need 7 inverse mod 15. I can use the Euclidean algorithm to find the inverse of 7 mod 15. That's actually what I have to do if the numbers were large. But now I'm just thinking out loud. Let me see. 7 times 2 is 14. That's negative 1. So 2 is almost the inverse of 7. It actually gives me negative 1 when I multiply by 7. So I'm thinking 7 inverse is negative 2 mod 15. Because if you multiply negative 2 by 7, it gives you negative 14, which is really 1. So negative 2 is actually, what, is that 13? So I'm going to use 13 in for the inverse of 7. So that gives me the value of k is 13 times 2 mod 15. 13 times 2 is 26. Mod 15, 26 is 11. So that means that k is 11 mod 15. Now I get the value of k 11. I'll stick it in here, and that will give me the value of x. Therefore, x is 3 plus 7 times 11, which is 80. And this actually is mod 105. X is 80. The thing is, if I use the next element, this next number, mod 15, I'll multiply it by 7 anyway, so the next x will be 7 times 15 times 1. And that's why. And now, let me just describe what the Chinese Remainder Theorem says. So the theorem says, if x is congruent to A mod n, and x is congruent to B mod m, and if the GCD of n and m is 1, then there is a unique solution. Mod n times m. The system has a unique solution, mod n times m. Okay? So how we solve it is just like the way, this is the how, not the proof of the theorem. How you solve the system is you first write x as a plus n times k for some integer k. Where I get this from is actually the first equation. A is x is congruent to A mod n. And now I'm going to stick this into the second equation. So A plus nk is congruent to B mod n, mod m. Okay, I'm putting it into the second equation. That means that nk is B minus A mod m. All right. So notice n and m, the GCD of n and m is 1. So n is invertible mod m. So I'm going to write k as n inverse times b minus a mod m. So basically what this recipe is telling me is find the inverse of n mod m and then multiply it by b minus a. That will give you the value of k. Once you get the value of k, put it back into this equation, and that will give you x. All right, take it.